friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
So design analysis and optimization of a helical coil heat exchanger using SolidWorks flow simulation, right? So let us model this first, then we'll go for design and analysis. Okay, first we have to model one helical coil, right? So for modeling, we start with top plane normal to, and we'll start from sketch circle. Let's draw a circle of any dimension. Provide smart dimension to this one as 1000 millimeter. So green check and exit from the sketch. Next select the sketch again and features. From curves we can start with helix and spiral. For helix and spiral we have different options. We'll select options pitch and height. We'll select, and height we are considering 1000 millimeter and pitch will be 200 millimeter and starting angle 270 degrees. We are considering clockwise. Okay, green check. So helix is done already, right? Now we have to provide profile to the end of this helix. So let's select the end of this path and we have to provide a plane on that location. So plane is provide normal to that path. So we made a plane normal to this path. Green check. Now on that plane we have to provide on a specific cross-sectional area. Okay, so we'll start sketching on that. Let's start with circles. Let's provide two circles of diameter 150 and 140 millimeter respectively. Smart dimension, this one 150 millimeter and the inner one 140 millimeter. Done. So drawing is complete. Green check and exit from the sketch. Next select the sketch again and features, sweep boss base. We have to select that path. Profile is already selected. We have to select the path for completion of this drawing. So our initial helix is ready. Green check. This is the helix, right? Okay, what we'll do is we'll save this one in a specific name. We'll save this one by the name of outer tube. It is saved. Next one we'll do one thing. With the same drawing we'll provide a different cross section to the same path, right? Let's save this drawing with a different name. Save as inner tube. Next one what we'll do is we'll change the cross sectional area. Select that sketch and edit that sketch. Now here in this sketch what we'll do is we'll change the cross sectional area with 100 millimeter and 90 millimeter, right? We'll change it. This one 90 millimeter and this one will replace with 100 millimeter. Green check and exit from the sketch. This is also done. This one we will save it by the name of inner tube. Okay, we have already saved it. Done. Now with these two different set of tubes we have to make our helical coil heat exchanger. Now these two things we have to assemble, right? So we'll start new assembly. Okay, and we have to bring these two. By browsing we can select all these things together. That will be inner tube and outer tube we have to select. So both the parts we have selected. In between these two components, the first one is fixed and the second one is floating. What we'll do is the first one will make it reversed. The first one will make it float. So this one can be floating and the this part will make it fixed. So select and make it fixed, right? Okay, now we have to assemble these things. For assembly you have to start with mate, and initially we know that for complete assembly we have to consider 3 different constraints. What we'll do is we'll take the 2 different planes to be aligned together, but at the same time we'll take the faces of their pipes. Okay, so we'll select the front plane of any one component, front plane of the inner pipe we have selected. Similarly, the front plane of outer pipe should be also selected. These 2 are aligned together, so these 2 different planes are assembled together. Okay, these 2 in the same plane, right? Next one, some other planes we have to align together. So we'll select right plane of the outer pipe, and that to align with the right plane of the inner tube. Green check, these 2 are aligned together. Now you can see these are aligned together, but it is not perfect. Still another constraint is required, right? So what we'll do is, for complete assembly we have to select the faces of these 2 again. So what we'll do is, the last constraint is required. Let us make this one a little bigger for proper selection. We'll select this face, and that should be aligned with the face of this one again. So make it little bigger and select this face. It is done. So all the 3 constraints have been satisfied, and we can see our assembly. This is our assembly, right? Done. You can see the mating faces, right? This is our assembly. Perfect. Now what we'll do is we'll change the material, and we have to provide some leads also. Assembly is complete. Now for providing material, we'll select, actually for this helical coil heat exchanger, 2 materials can be provided. One may be stainless steel and another may be copper. So in our case we'll consider copper as a material for this helical coil heat exchanger. So we'll select copper from metals. It will be copper. We're selecting polished copper, and that will be applied on both the components. So what we'll do is select these components separately, and that to be applied. So inner copper tube is selected and material is assigned already. Next one we'll select the outer tube, and copper is assigned to both the parts, right? For better understanding, we can make it little bigger, this edge. Okay, done. Now what we have to do is we have to provide some leads at the 2 different openings. Now you can see one thing, like for better understanding, let's see whether it is okay or not. We can cut the object from front plane. You can move it. See, this is our drawing. It's okay. You can see from any specific plane. Let's make it a little bigger and see whether it is okay or not. It appears everything is perfect, right? Okay. Let's select the complete view again. Now we have to go for analysis, that is flow simulation analysis. Initially, for starting this analysis, we have to create a closed volume. For creating the closed volume, we have to provide leads at the entry and exit points, right? As I told before, it will be like counterflow heat exchanger. Only the difference is the passage of water will be in the form of helical coil. Okay, the trajectory of the flow particles will be in the form of helical coil. So we can provide leads to these ends. Leads can be provided from flow simulation tools and create leads. For creating this, you have to select the surfaces. Let's make the size a little bigger. One lid is made. Now we can select the other face for making the other lid. We have made both the lids. Okay, the lids are ready. Next one, we have to go for analysis, right? So for starting SolidWorks flow simulation, we have to create an environment, and that environment can be created with the wizard itself, right? This is a model. Okay, now let's start our analysis, right? So starting from wizard, and by default we are starting with the project name as project 3. Next, and we are selecting the unit system as SI system and considering temperature as degree centigrade. Next, it will be an internal analysis, and we are not excluding the cavities because inside these cavities flow particles will be there, that will be water at different temperatures will be flowing inside this passage. So we are not excluding cavities. It is an internal analysis. We are considering heat conduction in solids. Heat conduction in solids only will not be there because we are considering heat conduction in solids, and inside these solids water at different temperature will be flowing. And gravity definitely will consider, and it will be, you can see the direction of gravity, it will be in the y direction. So the value of gravity will be in the y direction, will be minus 9.81 meter per second square, and in the z direction it will be 0 meter per second square. We consider liquid as water only, that means water at different temperatures will be flowing through this passage. Next, metals we'll consider as copper. For the outer, we'll consider a specific heat transfer coefficient at a specific temperature. Let the atmospheric temperature be 20 degrees centigrade, and at this temperature convective heat transfer coefficient will be 65 watt per meter square degree Kelvin. Next, we are considering the atmospheric temperature as 20 degrees centigrade, and then that of solid parameters temperature also 20 degrees centigrade. So finish it. You can see this is our computational domain. First of all, we have to make the domain hidden. Let's make the computational domain hidden. Next one, we have to provide that fluid domains, different subdomains to be provided for this fluid, because we are considering water at different temperatures. Hot water will be flowing inside this tube at temperature 100 degrees centigrade, and outside this hot water, cold water will be flowing at 10 degrees centigrade. So two different fluids at different temperatures will be flowing inside this helical coil heat exchanger. So we have to provide the domains of these different fluids. So we're starting with fluid subdomains, and for better location of these fluid subdomains, it is recommended to select a segmented view of this model. So we'll cut it along specific plane. We have cut already. Now it will be easier to provide that domain. Okay, actually hot water at 100 degrees centigrade will be passing through this down part of this inner tube, and cold water will be passing from the top part of the outer tube. Okay, so we are selecting the fluid subdomains. Insert fluid subdomain. It will be water at 100 degrees centigrade, so we'll select the temperature to be 100 degrees centigrade, and hot water will be passing through this location. So this is the fluid domain for hot water. Green check. Next one, we have to provide fluid domain for cold water. Again, fluid subdomains. Insert fluid subdomain, and cold water at 10 degrees centigrade will be passing through the outer jacket or outer pipe. So we have to select the location of that outer pipe. Let's make it a little bigger. we can provide the location of this cold water. It will passing through this one. It is showing the path of cold water. You can see from this face, this is the path of cold water at 10 degrees centigrade, and inside this one hot water at 100 degrees centigrade will be flowing. Okay, so we have already provided fluid subdomains. Next one, we have to provide solid materials. Let's provide solid material. Insert solid materials, predefined. It will be metals and copper. For both the inner and outer tubes, we have to provide this copper material. So selecting inner tube, by the same time we have to select the outer tube also, right? Both the tubes we have selected and the material is copper. Green check, so material is provided, right? Next one, you have to provide boundary conditions, right? We'll apply boundary conditions. That means hot water at 100 degrees centigrade will be passing from the bottom part of this inner tube, right? So we can make it little bigger for better understanding and better application of boundary conditions. Hot water at 100 degrees centigrade from here at a rate of 0.05 kg per second it will be flowing. So boundary conditions, insert boundary condition, water at a rate of 0.05 kg per second, and thermodynamic parameters will be 100 degrees centigrade. It will be passing from the inner tube. Green check, one boundary condition is applied, right? Next one, by the same location, hot water exit it will be there. So as I told that hot water will be passing from top outer pipe, and this location will be the exit of hot water, right? So we can apply boundary condition again. Boundary conditions, insert boundary condition. It will be atmospheric pressure at this location. This one will be for cold water exit location. Okay, select that location, green check, done. Now two more boundary conditions are required at this location. Let's make it little bigger for better application of boundary conditions. So boundary conditions, insert boundary condition, cold water at 10 degrees centigrade and at a rate of 0.05 kg per second. Let's provide the thermodynamic parameters. It will be 10 degrees centigrade. Cold water at 10 degrees centigrade will be flowing from outer pipe at this location. Select that location, green check, it is done. Now the last boundary condition, that means the exit of hot water will be equal to atmospheric pressure that will be applied here at this location. So boundary conditions, insert boundary condition, atmospheric pressure at the exit of hot water, select, green check, it is done. All the boundary conditions have been applied properly. Now we have to select some goals, right? We have to consider some surface goals. Let's select goals, insert surface goals. We want to find average temperature of fluid at the exit ends for cold water and hot water also, both cases, right? So we are selecting average temperature of fluid at the exit of hot water at this location. Green check, one goal is defined. We can rename it as average temperature of hot water. Similarly, another goal will be required, that means average temperature of cold water at the exit, right? So to select that location, So selecting another goals, insert surface goal. Going to find out average temperature of fluid at the exit of cold water at this location. Green check. So both the goals have been defined. You can rename it as average temperature of cold water at exit. Similarly, the first one we can change it also, rename it as average temperature of hot water at exit. So both the goals have been defined properly. Now we can run this. Let's run it. Model preparation is going on. Let the iterations move on. Whenever it is finished, we'll see our results and go for analysis. Okay. The solver window has finished its calculations. Now you can see our results from here itself. Like you can see here that this is the passage of flow trajectory of water particles. From here you can see hot water is passing from the inner pipe. The red color represents the temperature of water is 100 degrees centigrade. At the bottom part, we have fed hot water from the bottom and cold water from the top one, right? You can see here in the inner pipe, temperature of hot water is 100 degrees centigrade, and as it is approaching towards the top, its temperature is also changing, and its temperature change is also indicated by the change of color itself. You see initially temperature of hot water was 100 degrees centigrade, and as it is going up, its temperature is changing from yellow to green and finally again reddish yellow, right? You can see green means it is in the range of near about 90 degrees centigrade. So from bottom to top, inside this inner pipe, hot water is flowing and its temperature is ranging from 100 degrees centigrade, and finally it has gone in the range of 90s, right? Near about 94, 5 something else. It is in the range of 90s. Similarly for cold water, we can see cold water is started from top, and from top to bottom it is coming down. Initially cold water temperature was in the blue range, that means 10 degrees centigrade, and as it is approaching down, its temperature is increasing. You can see from blue to light blue actually, right? And light blue means it is in the range of 15 degrees centigrade. Okay, all these things we can see from here also. From goal plots, we have decided to find two goal plots. Let's see the goal plots. See, we have started two things like this: average temperature of cold water at exit and average temperature of hot water at exit. You can see that it has undergone how many numbers of it? It has undergone near about 250 numbers of iterations, and after 250 numbers of iterations, you can see the average temperature of cold water at exit equal to 14.91 degrees centigrade. Similarly, average temperature of hot water at exit equal to 93.62 degrees centigrade. Right? These are the results obtained from our solver window. Okay. Now we'll see the results from the cut plots. We can see our results. Cut plots. Insert cut plots. We want to see from front fence, and we'll see the temperature of fluid. Green check. For viewing these things, we have to make the model transparent, right? So first of all, we have to make the model transparent. Let's go back to the geometry and make it transparent. Select the inner tube and let's make it transparent. It is done. And again, we have to select the outer part also. Select the outer tube and let's make it transparent. It's done. Now you can see the cut plots. This one we have already seen in the solver window, right? We can see these things in the form of an animation. That will be a better one. So cut plots, cut plot 1, let's play. You can see the temperature distribution of fluid inside this helical coil heat exchanger. It is showing the trajectory of hot and both cold water inside this coil, right? From the bottom it is red zone, that means temperature high is 100 degrees centigrade, and as it is approaching top, its temperature is reducing. Similarly for the cold water also, as it is approaching from top to bottom, its temperature is increasing. Initially at the top for cold water, its temperature was 10 degrees centigrade, and as it is approaching down, its temperature is increasing and final temperature is 15 degrees centigrade approximately. Okay, let's clear and hide this part, and we'll see surface plots. Clear and hide this part, and we want to see surface plots. It will show, and at any specific surface we can see insert surface plot. We can see the pressure, temperature, velocity, etc. at any specific surface, right? Let's select along all surfaces, and we want to see temperature of fluid. It is showing that out of periphery, that means the cooling jacket, it is having temperature in the range of, like you can see the blue color, that means in the range of near about 15 degrees centigrade, and inside this pipe, that means inner tube, this temperature is having in the range of 90 to 100 degrees centigrade, right? You can see from bottom it is completely red, that means 100 degrees centigrade, and as it is approaching towards the top in the helical way, and final its temperature is in the range of 94 degrees centigrade. You can see here clearly it is having mixed zone, that means it is having both yellow, red and also reddish yellow zone. So its average temperature at the exit of hot water is near about approximately 90 degrees centigrade. Okay, done. What we'll do is, next one, let's clear and hide this part. Surface plot 1, clear and hide. Next one, we want to see flow trajectories, that means how the hot water particles and cold water particles will be moving. You can see their trajectories, right? So flow trajectories, insert, and instead of 20 numbers we want to make it more, maybe it will be 200 numbers, and we want to see in the form of arrows only. Okay, we have to provide the location of hot and cold water particles. So hot water will be passing from the bottom part of inner tube. Let's make it a little bigger for proper selection of this location. Select other. This is the location of hot water particles at 100 degrees centigrade. Similarly, you have to select the location of cold water at 10 degrees centigrade from the top part. Okay, so let's make it a little bigger. Select other, face, extrude face, green check. We have selected the different regions for these hot and cold water particles. Particle study is running right now. You can see the flow trajectories with different colors. It is clearly visible that water particles were moving from bottom to top. At the bottom part, its color is red, that means its temperature is 100 degrees centigrade, and as it is moving up in the form of an helical coil, at the top part its temperature is decreasing and final temperature is in the range of 90 degrees centigrade. Right, similarly cold water also is coming from top to bottom. I can make it a little bigger. Cold water, it is blue region and it is passing from top to bottom, and at the bottommost part its color is in the range of light blue, right? So better to see this one in the form of an animation. So what we'll do is, let's clear and hide this part, and I will show it in the form of an animation, right? Let's play it. Flow trajectories you can see in the form of an animation. So it is moving. Better you can see in a bigger way. You can see how the water particles are moving from bottom to top and from top to bottom also. This is the flow trajectories, and outside this is the cold water, this cooling jacket, right? We can edit this part little bit. If we make this particle size little small, then also it can be viewed properly. We'll make it little smaller, particle size, flow trajectories, clear and hide. I will make it little smaller, edit definition, and let's make the size of these particles little smaller, green check. Now we'll see this one in the form of an animation. Flow trajectories, clear and hide. Again, let's play it. Fine droplets of water particles at 100 degrees centigrade and 10 degrees centigrade are moving from top to bottom, right? From bottom, 100 degrees centigrade water from the inside pipe is moving from top to bottom in the form of one helical way. The flow trajectory is helical path, and cold water, again it is passing from top to bottom at the outer jacket surrounding this inner pipe. Okay, this is the trajectory of water particles. Let's clear and hide this part. Flow trajectories, clear and hide. Next one, we'll see our results in the form of goal plots. Goal plots, insert, and we had two goals. Insert goal plots. We'll see all the goals and show it. You can see the results what we have already seen from our Solver window. You can see that average temperature of hot water at exit is 93.62 degrees centigrade. Its minimum temperature is 92.74 and maximum is 95.46 degrees centigrade. Similarly, for cold water, its minimum temperature is 14.72 degrees centigrade and maximum is 14.93, and its average is 14.91 degrees centigrade, right? This is our goals. Now for better analysis, we can take this data in the file and go for perfect analysis. We can go for optimization also. Suppose in this result you can see that our temperature of hot water exit equal to 93.62 degrees centigrade and cold water exit is 14.91 degrees centigrade. Suppose we want to get the hot water exit temperature to be 90 degrees centigrade. For that we have lot of different options. We can change the input variables, we can change the dimensions of different pipes, we can change the length of these different pipes, or we can change the input variables in the form of boundary conditions also. That means we can change the temperature of cold water also, right? These are the different options available. Now what we'll do is we are planning to optimize the temperature of hot water to be 90 degrees centigrade, and for getting this 90 degrees centigrade hot water exit temperature we have to depend on some other variables. Let's select the input variable as the cold water temperature, right? So we're going for some kind of different optimization. Before going to optimization, we'll go for some kind of parametric study. So we have to find the specific range for cold water to get this optimum temperature. Okay, so we're going for parametric study, going for new parametric study, and in this case we'll consider design experiments and optimization, and for that it will depend on some input variables. Let's select the input variables in the form of this cold water temperature, right? We want to select cold water as the input variable. It will come from boundary conditions, inlet mass flow rate, we want to change it, initial temperature of water was 10 degrees centigrade, that one we want to change it. Let's select the temperature from 10 degrees centigrade to something else. Okay, green check. So we have to select the range of cold water, right? We'll select this one. Let's select the range from 0 degrees centigrade to 9 degrees centigrade. We're specifying the range of cold water, and we'll see that within this range whether the exit temperature of hot water will be 90 degrees centigrade or not. Okay, green check. Let's see the scenario. 5 numbers of experience we are selecting. Let's create that different scenarios. That means at a different cold water temperatures, we'll try to find out the exit temperature of hot water. From this range you will have an idea, and from that idea finally we'll go for optimization, right? Let's run these iterations. It will take some time for these iterations. Whenever it is finished, we'll see the results. Iterations for parametric study has already been finished. You can see our results from parametric study, that with specific input variables we wanted to have an idea about our goal. We have selected a temperature range of cold water from 0 degrees centigrade to 9 degrees centigrade, and based on that we got the exit temperature of hot water. You can see that at 0 degrees centigrade of cold water, our exit temperature of hot water is 93.74 degrees centigrade. At 2.25 degrees centigrade cold water, exit temperature of hot water is 93.64. At 4.5 degrees centigrade, the result is 93.63, and at 9 degrees centigrade of cold water, the temperature of hot water exit is 93.95 degrees centigrade. So from this parametric study, got an idea that cold water temperature is not a predominant input variable for changing the output temperature of hot water. That means this cold water temperature cannot provide our goal, right? So to have our goal, we have to depend on some other variables. So in this way, with parametric study, we can decide which one is more predominant to have our goals. Now we can do another thing, like we can vary the dimensions of this coil. That means we can change the diameter, even the length of this coil to have our goal. Instead of stopping it here, we can go for different types of parametric study using different input variables and perform similar type of parametric study, and based on that we can have specific range of input variable, and with that input variable we can go for finally optimization, right? So this is all about our today's analysis of helical coil heat exchanger using SolidWorks flow simulation. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.